what is force field? Does force field really exist? Certainly yes. A field is a region where no contact force acts on the object. There are three different types of fields, namely the gravitational field, the magnetic field, and the electric field. A field is a region where non-contact force is experienced. Most forces we experience in everyday life requires contact, but in all of the above, no contact is required. Everything we see is made up of millions of atoms, so small that our eyes cannot see them. Each atom is made of even smaller particles. In the center of the atoms, there are the protons and the neutrons. Surrounding them are the electrons. The protons are positively charged, and the electrons are negatively charged. Most matter are neutrally charged, meaning the number of protons and electrons are the same. When atoms has more electrons than protons, it becomes negatively charged. When atom has less electrons than protons, it becomes positively charged. Alright guys, I need you to get me two things. Piece of transparency and some tissue paper. Hey, go get it, I'm waiting. Alright, you have got it? Good. I want you to now tear your tissue paper into small little shreds like this. Okay. With your transparency, rub against your clothing about 20 times. Okay, and place over the tissue paper. Woohoo! That's electrostatic force. So what's happening? Some materials hold electrons more tightly than others. The transparencies hold electrons better than the cotton. When the two materials come into contact, the transparency's atoms took electrons from the closed atoms. The transparency is now charged up. So is it negatively or positively charged? That's right, it's negatively charged because it has more electrons than protons. So the clothing is positively charged. Now that you have seen that transparency can be charged by friction, let me introduce you to this Van de Graaff generator. When the motor is turned on, the roller begins turning the belt. Electrons are transferred from the belt to the roller just the way that electron was transferred when I rubbed the transparencies against my pants. The positively charged belt will in turn remove electrons from the sphere, causing the sphere to be positively charged. We have already seen the effects of electrostatic force. So what are the factors affecting the magnitude of the force? Right here I have a small positively charged sphere. As I turn on the Van de Graaff generator, the sphere will become more and more positively charged. Let us observe what happens. Notice the angle of the tube increases as the positive charge on the sphere accumulates. This shows that the force is actually dependent on the amount of charge stored on the sphere. Okay. Next, we are going to observe how the force depends on the distance between the two spheres. As I move the ball nearer and nearer to the Van de Graaff generator, notice how the angle of tilt changes. When the distance between the two charges is smaller, electrostatic force becomes larger. In fact, the force is inversely proportional to the square of the distance between them. In 1780, the French physicist Charles Coulomb concluded that the force between the two charged objects is proportional to the magnitude of each charges and inversely proportional to the square of the distance between them. field is a region where non-contact force is experienced. Electric field is defined as the resultant force per unit positive test charge. The steel sphere is going to tap positive charge from the Van de Graaff generator. We are going to investigate the electric field of this positively charged steel sphere by placing a small positive unit test charge near it. What do you think will happen to the test charge when we switch on the Van de Graaff generator? That's right, the test charge is repelled because like charges repel. What is the direction of the E field at this point due to the steel sphere? Remember, E field is defined as the resultant force per unit positive charge. So, the direction of the E field is pointing away from the steel sphere. In order to visualize the electric field, we draw a series of lines to indicate the direction of the electric field at various points. These, we call it the electric field lines. How do we draw the electric field lines of this steel sphere? We can place small positive test charge around it. Positive test charge placed in the electric field of the steel sphere will be repelled by its positive charge. The lines are directed radially away from it. The steel sphere is now negatively charged. Can you draw electric field lines of this steel sphere? Again, by mapping the line of force experienced by the positive test charge, the electric field lines can be determined. What is work done? Work done is the product of the force and the displacement in the direction of the force. As I move the ball upward at constant speed, is the work done by my hand positive or negative? That's right, it is positive because I am applying an upward force to oppose the weight that is downward, and the displacement is also upward. So, the direction of the force is in the direction of the displacement, and work done is positive. As I move the ball downward at constant speed, is the work done by my hand positive or negative? Yes, it is negative because the force applied by my hand is still upward. However, the displacement is downward. They are both in opposite direction, so work done is negative. As I move the ball across at a constant speed, is the work done positive or negative? If your answer is positive or negative, you are wrong because there is no work done. The force is upward, but the displacement is horizontal. The force and distance are perpendicular each other, there will be no work done. Both the Van de Graaff generator and the ball are positively charged. The repulsive force is evidenced from the angle of the string. What is the work done by the hand as we move the ball towards the Van de Graaff generator at constant speed? That's right, it is positive because the force by my hand is in the same direction as the displacement. Likewise, as I move the ball away, the work done is negative because the force by my hand is opposite to the direction of the displacement. As I move the sphere away from the Van de Graaff generator, we can see that the force now becomes insignificant. So we can assume that the potential energy due to the Van de Graaff generator to be zero. As I move the sphere towards the Van de Graaff generator, it is gaining potential energy because I am doing work on the sphere. As I move to this distance here, you can see that the force of the repulsion is relatively small. So I can say that my work done is also quite small. As I move the same distance towards the Van de Graaff generator, I am doing significantly more work because the repulsion force becomes more significant. Since the force is not a constant, so work done will be given by the integral of F ds. So, By referring to the appendix, you can look at the derivation for the potential energy. The potential energy is given by the formula KQQ over R. The potential is defined as the work done to bring a unit positive charge from infinity to the point. Since potential energy is given by the formula KQQ over R, we can cancel out the Q to get potential V equals to KQ over R. The voltmeter can be used to measure potential difference. We are going to use the voltmeter to measure the potential difference across 2 points within the electric field of the Van de Graaff generator. Because of the high voltage involved, the readings here will indicate kilovolts. Now let us take a look at the setup. Over here we have the Van de Graaff generator. The 2 pins here are the terminals of the voltmeter. Now as you can see from the voltmeter reading that when the 2 terminal is far away, there is no potential difference between the 2 points. As I start to move at a very far distance from the Van de Graaff generator, the values remain 0. But as I move closer and closer to the Van de Graaff generator, take note that the values starts to increase, because the potential difference between these 2 points is higher. As I move the black terminal towards the Van de Graaff generator, notice that the value again decreases. So we can say that the potential difference between these 2 points is about 20 volts. So the potential difference at this point is about 32 volts. Now as we move to different points about the same distance away from the Van de Graaff generator, you can see that the potential difference remains approximately a constant. So we call these points equal potential point. If I continue to map out this line, we will call it the equipotential line. We have come to the end of the electric field e-learning. Have you enjoyed the video? I hope it has been a fruitful learning experience for you. See you soon.